Hello. In the previous video, we studied the method of Lagrange multipliers for function of two variables. Today, we'll solve a couple of problems for function of three variables, and then we will study the method of Lagrange multipliers with two constraints. All right. Before that, I would like to remind you the main idea of the method of Lagrange multipliers for function of two variables. So if we remember, last time we studied, following problem. We have an ellipse, right? And we consider all rectangle inscribed in the ellipse, and we need to find the maximum area of this rectangle, right? That means we have to find x and y such that the area is maximum, and the equation of the ellipse is x squared over 9 plus y squared over 16 equal to 1. So this is our constraint. This is our constraint, right? And we set up the area function. The area function is for x and y. So we need to maximize this function. And we already discussed, in this case, partial derivatives will not help. But we consider this problem from the point of view of level curves. So I will consider different level curves of this function. And this level curve is nothing but hyperbolars. So I put that is y equal to k over 4x, right? So those curves look like this. And then we move these curves along, for different k, right? For different k. And we understand that, when this curve is tangent to the ellipse, the function attains maximum. So that's why we need to find that point, right, where two curves are tangent. And how to find that? The main idea is, when two curves are tangent, their normal vectors are scalar multiple, right? The normal vector are scalar multiple. And lambda in this case is called the Lagrange multiplier. So if we move to function of three variables, we will talk about level surfaces. The idea is almost the same. We still have this, right? We still have this picture, but for surfaces. So basically, for function of three variables, I will have this equation together with the constraint. Make sense? Let's find gradient of f and g. So we have gradient of f equal to 4x, 2y, and then 6z. While gradient of g is 2, -3, and -4. From here I have 4x equal to 2 lambda, 2y equal to -3 lambda, and 6z equal to -4 lambda. That comes from this equation. Okay, so together with the constraint, we will solve a system of equations. So from the first one, I have lambda equal to 2x. From the second one, I have lambda equal to 2y over -3. From the third one, I have lambda equal to 3z over -2. And I have relations between x and y and z. I will use this relation and the equation star, which is the constraint, to find x and y and z. So I have y equal to -3x and z. You solve this, you get y equal to -3x. You solve this, you get z equal to -4x over 3. Okay, and then you plug everything into the equation star, which is a constraint. You get 2x minus 3, negative 3x, and then minus 4 times negative 4x over 3. And this is equal to 49. Now we solve for the x, and then we plug back here to find y and z. 2 here we have 9, so I have 11x, and here I have 16 over 3x equal to 49. So basically I have 33 plus 16 divided by 3x equal to 49, and x equal to 3. Perfect. Now I plug x equal to 3 into this to find y and z, right? To find y and z from here. Oh, actually we already have them in here. So from here I get y equal to negative 3 times 3, which is negative 9. And then z equal to negative 4 times 3 over 3, which is negative 4. All right. So we already have the point x equal to 3, y equal to negative 9, and z equal to negative 4. If you want, you can find lambda, the Lagrange multiplier. But if they just ask you to find the minimum, you just plug x and y and z into the function. And your function is f of x and y and z equal to 2x squared plus y squared plus 3z squared. At this point, you have 2 times 3 squared plus negative 9 squared plus 3 times negative 4 squared, and in the answer you would get 147. So that is the solution. So I think everything is okay. The only thing we need to pay attention is this equation. Is this equation. That is the main idea. You know, for function of 2 variables, for function of 3 variables, or for function of n variables, you use the same method. So the gradient of f is scalar multiple of the gradient of g. Make sense? All right, let's move to the next example. We have function f, x and y equal to x squared plus 2y squared minus 2x plus 3. Okay, and the constraint x squared plus y squared less than or equal to 10. This is the constraint. We need to find extreme value of f, x and y. What is the difference between this problem and previous problems? The difference is right here. The constraint is less than or equal to 10. That means not only on the circle, but the domain is the constraint is everything inside the circle, right? Because that is the equation of the circle. So I can write like this. We have the radius is square root of 10. So that is the whole constraint, not only on the circle, but everything inside the circle. So how to do with that? You know, the method of Lagrange multipliers helps us to find maximum or minimum on the border. Is it correct? On the border. Which is good. And if we use partial derivatives and second derivative test, so we will see the extreme values inside. So everything inside here you can solve using partial derivative. So if you compare two methods, you can solve this problem. Make sense? Before we move to the solution, I would like to mention one thing, right? I want to compare a little bit between calculus 1 and calculus 3. In calculus 1, you solve the problem extrema, global extrema on some closed interval, right? So you find all critical points in here, all critical points inside that interval, and then you compare function values at those critical points and at two endpoints. But if you consider function of more than one variables, there's no way to calculate the function values at all points on the boundary. Make sense? So that's why we need Lagrange multipliers. And once you have Lagrange multiplier method and you know critical points, you just need to compare function values. So let's solve this problem. Let's find partial derivatives of the functions, right, f. So I have f with respect to the x is 2x minus 2, and f with respect to the y is 4y. And we set them equal to 0 to find critical points. From here we get x equal to 1 and y equal to 0. So we have only one critical point, right? Where's that? X equal to 1, y equal to 0. This somewhere right here, inside the circle, right? 1 and then 0. We don't have any critical points on the circle, but inside the circle we have 1. So in order to find global axioma of the function, we need to compare the function values at this critical point, right? And the axiom values on the boundary. Okay, so we finished with the critical points. Now we need to use Lagrange multiplier method to find the maximum and minimum values on the boundary. Okay, so we need to have the function g xy, that is x squared plus y squared minus 10. Okay, and you calculate the gradient of g, which is 2x and then 2y, and then you set the following equation: gradient f equal to lambda gradient of g. That means 2x minus 2 and then 4y equal to lambda 2x and 2y. You see, from here you can simplify 2. Okay, anyway, let's write it down. You have x minus 1, 2 in here, equal to 2 lambda x, and then 4y equal to 2 lambda y. Okay, so it's interesting. From the second equation, you will see the y equal to 0, right? Or the lambda equal to 2. Make sense? So if the y equal to 0, you can plug this into the constraint. You plug this into the constraint, which is x squared plus y squared equal to 10. And from here you can solve x squared equal to 10 or x equal to plus minus square root of 10. Make sense? And you have 2 points on the boundary already. That is the first case when y equal to 0. The second case when lambda equal to 1. So when lambda equal to 2. And you plug lambda equal to 2 into this equation. You have x minus 1 equal to 2x. Or x equal to negative 1. Once you have x equal to negative 1, again you will plug this value into the constraint, right? So you have x squared plus y squared equal to 10. And from here you can solve for y, that is 10 minus 1 squared, which is 9. And y equal to plus minus 3. Okay, let me summarize this. So what points we get, right? The first is x equal to plus minus square root of 10 and y equal to 0. So I will copy it right here and y equal to 0. We have 2 points, right? In this case. And in the second case, we have other 2 points when x equal to -1 and y equal to plus minus 3. So basically, I'll copy right here, y equal to plus minus 3. So on the boundary, we have 4 points, right? And now, the last step is to plug the coordinates of these 4 points into the original function to find the function values and compare with the function value at the critical points that lies inside the circle. All right? X and y here. And here's the function fxy. The first point is -1, 3, -1, -3, and then square root of 10, 0, and then negative square root of 10, 0. Those are 4 points, and the only critical point inside is x equal to 1, y equal to 0. You plug in the function. Okay, let me copy the function right here so it's easier to follow. I have x squared plus 2y squared minus 2x plus 3, right? So at -1, 3, I get, I plug -1 in here and 3 in here. I get -1 squared plus 2 times 9 minus 2 -1 and then plus 3. So you get 18. You get 2, you get 3 plus, and you get 1 in here. That is 24. So the function value in this case, 24, okay? At -1, -3, you should get the same number, right? Because here you have y squared, so there's no difference between 3 squared and -3 squared. X square root of 10, 0. So y is 0, x is square root of 10. You get 10 minus 2 square root of 10 plus 3. And, just calculate this number. So I would write here just 13 minus 2 square root of 10, okay? And at -10, you would get 10 in here, and then minus plus 2 square root of 10 plus 3. So I get 13 plus 2 square root of 10. And at 1, 0, you plug 1, 0 into this function, you get 1 square minus 2 and then plus 3, which is 2. So now you compare all these values. All right? And you see actually the smallest one is this guy. That is the minimum. And the biggest one is at these 2 guys. So that is your maximum. Okay? So see, yeah, this problem is a little bit long. But, if we have some constraint like this, we need to compile 2 methods. The method of Lagrange multipliers and then with partial derivatives. Make sense? All right, so I think we already have 2 problems with function of 2, 3 variables. And one is with just Lagrange multipliers. Another one is global extrema. Now let's move to the method of Lagrange multipliers with 2 constraints. Let's consider the function t, x, y, z equal to 20 plus 2x plus 2y plus z squared. And x and y and z satisfy the following constraints. The first one is x squared plus y squared plus z squared equal to 11. That means we consider points on the sphere, right? Central at the origin and the radius equal to square root of 11. And the second constraint is x plus y plus z equal to 3, which is a plane. Make sense? And they ask you to find the extreme value of t, subject to the constants 1 and 2. So how to solve such a problem? With one constant, everything is clear enough because now we already know how to do that. If we have two constants, we have to find the extreme values of t, right? The extreme values of t. Not on the sphere, not on the plane, but on the intersection between the sphere and the plane. Okay? So, the situation is a little bit different. So, we have more constraints, so we have more restrictions. Make sense? In that situation, we still can use the method of Lagrange multipliers, but with some modification. So I would say, yeah, this is your function f, x, y, and z. This is your function g, x, y, and z. And we have gradient of t is equal to lambda gradient of f plus beta gradient of g. So how to understand this equation? What does it mean, linear combination of two gradients in here? What does it mean? That means the normal vector gradient t is just a linear combination of normal vectors gradient f and normal vector gradient g. Because you have two constants in here, right? You have two surfaces in here. So for two surfaces, you would have two normal vectors. Make sense? And then you move your level surface such that, they intersect at that point. So basically, normal vector of the level surface of the function t is linear combination of normal vectors of the surface with respect to the f and normal vector of the surface with respect to the g. That's why you have this equation. Make sense? Now we have to find gradient of f, gradient of g, gradient of t, and plug into this equation. Together with two constants, we will find x and y and z, lambda and beta. Okay? All right, let's do this. Let's find gradient of t. That is 2, 2, and 2z. Gradient of f is 2x, 2y, and 2z. Gradient of g is 1, 1, and 1, which is good. And now you plug everything into this equation. You have the following: 2, 2, 2z equal to lambda, 2x, 2y, 2z plus beta, 1, 1, and 1. So if you write this down, you have the following equations. 2 equal to 2 lambda x plus beta. That is for the first coordinate, right? For the second coordinate, you get 2 equal to 2 lambda y plus beta again. For the last one, you get 2z equal to 2 lambda z plus beta. So basically, you have three equations, right? Together with two constants: x squared plus y squared plus z squared equal to 11, and then x plus y plus z equal to 3. You have a system of 5 equations. and 5 variables, x, y, z, alpha, and beta. Solving this system, you get x, y, z, lambda, and beta. And of course, you already have x, y, and z in here, right? And that is the point of extrema. Let's solve this system, okay? So let's say that is 1, that is 2, that is 3, that is 4, that is 5. You can subtract 1 and 2. You get 2 lambda x minus y equal to 0. From here, lambda equal to 0 or x equal to y. Again, we have two cases, right? For the case when lambda equal to 0, for this case, lambda equal to 0, you get beta equal to 2, right? You get beta equal to 2. And you plug this into the third equation right here, you see? From there, you get z equal to 1. Okay, so you plug z equal to 1 into the 4 and the 5, right? You plug into the 4 and the 5, you get x squared plus y squared plus 1 equal to 11. And x plus y plus 1 equal to 2, equal to 3. You solve this system for x and y. You get x squared plus y squared equal to 10. And x plus y equal to 2. It's easy to solve, you know, from the second equation. You get x equal to 2 minus y, and you plug this into x squared plus y squared equal to 10. So you get 2 minus y squared plus y squared equal to 10. And then that is y squared minus 4y plus 4 plus y squared equal to 10, or 2y squared minus 4y minus 6 equal to 0. So from here you get y squared minus 2y minus 3 equal to 0. And this is quadratic equation. You can use the formula, right? But in this case, this equation has special solution, which is y equal to negative 1, right? And y equal to 3. So basically, for the first case, when lambda equal to 0, you have 2 points. Z equal to 1, y equal to negative 1. And then, of course, you need to find x, right? I'm sorry. You need to find x. You plug this into this guy. You plug y equal to 3 into this guy to find x. So from here, I get x equal to 2 minus negative 1 is equal to 3. And from here, I get x equal to 2 minus 3 equal to negative 1. So basically, you have 2 points. 3, negative 1, and 1, where z is 1, right here. Okay, and another point is negative 1, 3, and 1. So that is the first case. You see, it's pretty long, right? For lambda equal to 0. For the second case, x equal to y. Means we have to solve this again, right? We have to solve the system again with x equal to y. So I have the following system. 2 equal to 2 lambda plus beta, lambda x plus beta. And then 2z equal to 2 lambda z plus beta. 2x squared plus z squared equal to 11. And then 2x plus z equal to 3. Because x equal to y already. Now we can use the last two equations to solve for x and z. So from the last equation, I had z equal to 3 minus 2x. And then I substitute this into the previous equation. I get 2x squared plus 3 minus 2x squared equal to 11. So I have 2x squared plus 9 minus 6 minus 12x plus 4x squared equal to 11, or 6x squared minus 12x minus 2 equal to 0. Or we can simplify, we write 3x squared minus 6x minus 1 equal to 0. Again, we need to use quadratic equation formula. Again, we need to use quadratic formula. So we have x1 and 2 equal to 6 plus minus square root of 6 squared plus 4 times 3. And here we have 2 times 3. Okay, so what is that? That is 6 plus minus 36 plus 12 over 2 times 3. That is 6 plus minus square root of 48 over 6, right? I think we can simplify a little bit in here, because 48 is what? 48 is 4 times 12, right? 4 is 2. Square root of 4 is 2. So I get 6 plus square root, plus minus 2 square root of 12 over 6, which is 3 plus minus square root of 12 over 3. All right, so that is x. We have two values of x. So that means we have two values of z, right? We plug this guy back here to find z. Okay, let's do that right here. So I have z equal to 3 minus 2. 3 plus minus square root of 12 over 3. We get 3. We get 9. Here's 3. 9 minus 6 plus minus 2 square root of 12. So basically that is 3 plus minus 2 square root of 12 over 3. It is pretty long. Okay, so we have z. We have x right here. I have to justify this. Here we should write negative plus. Makes sense? Because if you have plus minus in here, and then you have, with the plus you have negative, with the minus of x you have plus z. Okay, so basically we have 4 points. Oh my goodness. We have 4 points. That is x, and at the same time that is y. Okay. So for the second case we have 2 points. For the first case we have 2 points. Overall we have 4 points. Let me write them in here. That is 3 plus minus square root of 12, 3. 3 plus minus square root of 12, 3. And the z is 3 minus plus 2 times 12 over 3. So 4 points. The last step is to find the function values at those 4 points. You see, and from here I need to find f of 3, negative 1. No, not f, a t. And from here I get t, negative 1, 3, and 1. And from here I get t of those values. And it turns out that this value is 25, this value is 25, and these two guys is approximately equal to 30.33. So you can see that actually this is the minimum and this value is maximum. So we are done for this problem. It is very long. Probably I will not give you such a problem on the test, but we have to understand the idea. How to use method of Lagrange multipliers with two constraints. So that is the main idea. Okay? So hope that you enjoyed the video. If you have any questions, feel free to let me know.